Introduction to solar energy, harnessing the power of the sun. Solar energy technology allows us to capture and utilize the immense power of the sun. Solar panels convert sunlight directly into electricity through a process called the photovoltaic effect. The sun is an incredibly abundant source of energy, delivering more power to Earth in 1 hour than humanity uses in an entire year. Solar power represents one of the cleanest, most sustainable energy sources available today. Solar installations are growing rapidly worldwide as technology improves and costs continue to decrease. As we continue exploring solar technology, we'll see how these remarkable systems work at a fundamental level. The photovoltaic cell is the fundamental building block of solar panels. Each solar cell is made of semiconductor materials, primarily silicon, arranged in layers. These layers include a positively charged p-type layer and a negatively charged n-type layer. Where these two layers meet, a p-n junction forms, creating an electric field between the silicon layers. When sunlight hits the cell, it energizes electrons, which are forced to move by the electric field, creating an electric current. Multiple photovoltaic cells are connected together to form a complete solar panel. This p-n junction is crucial for the photovoltaic effect, enabling solar panels to convert sunlight into usable electricity. The photovoltaic effect is the process that converts sunlight directly into electricity in solar cells. When sunlight hits a solar cell, photons, which are particles of light, transfer their energy to the semiconductor material. These photons carry energy from the sun to the solar cell. This energy allows electrons to break free from their atoms and move through the material. The electric field at the p-n junction forces these free electrons to flow in a specific direction, creating an electric current. This phenomenon, discovered by Edmund Becquerel in 1839, is the fundamental principle behind solar electricity generation. Individual solar cells typically produce only about 0.5 volts of electricity. To generate usable power, many cells are wired together into panels. And multiple panels form arrays. These arrays increase the total power output of the system. These arrays are connected to inverters that convert the direct current electricity produced by the panels into alternating current electricity used in homes and businesses. This modular design allows solar systems to be scaled from small residential installations to massive utility-scale solar farms. Let's explore the main types of solar cell technologies currently available. There are three primary types of solar cell technologies used in photovoltaic systems today. Monocrystalline silicon cells are made from single silicon crystals, giving them a uniform, dark appearance. These cells offer the highest efficiency, converting 18 to 22% of sunlight into electricity. Polycrystalline silicon cells are made from multiple silicon fragments melted together. They have a distinctive fragmented blue appearance and offer slightly lower efficiency at 15 to 18%, but at a more affordable price point. Thin-film solar cells are created by depositing thin layers of photovoltaic material onto substrates like glass or plastic. They're less efficient at 10 to 12%, but are flexible and potentially less expensive to manufacture. Let's compare these three technologies based on their key properties. Monocrystalline cells offer the highest efficiency, making them ideal for limited space applications where maximum power output is needed. Polycrystalline cells provide a good balance of cost and performance, making them popular for both residential and commercial installations. Thin-film technology excels in applications where flexibility is required, such as curved surfaces or portable solar chargers. As solar technology continues to advance, researchers are developing new materials and manufacturing techniques to increase efficiency and reduce costs across all cell types. Several factors affect how efficiently solar panels convert sunlight to electricity. Solar panel efficiency is measured as the percentage of sunlight energy converted into electrical energy. Let's examine the key factors that influence a solar panel's efficiency. The type of semiconductor material used affects how much light can be converted to electricity. proper orientation and tilt, maximize sunlight exposure throughout the day and seasons. Even partial shading can significantly reduce the output of an entire panel or array. Higher temperatures actually reduce solar panel efficiency, contrary to what many expect. Dust and dirt accumulation can block sunlight, reducing energy conversion by up to 25%. Modern commercial solar panels typically convert between 15 to 22% of sunlight into electricity. Laboratory prototypes have achieved over 40% efficiency using advanced materials and multi-junction designs. The theoretical limit for certain solar technologies approaches 68%, showing significant room for future improvement. Higher efficiency panels produce more electricity in the same amount of space, but generally cost more upfront. For most residential and commercial installations, the balance between efficiency, cost, and available space determines the optimal choice. Solar panels produce direct current or DC electricity, but most homes and the power grid use alternating current or AC electricity. Here we can see the flow of DC electricity from the solar panels. Home appliances and the power grid, however, require AC electricity. This is where inverters come in. An inverter is a crucial component that converts DC electricity from solar panels into AC electricity that can be used in your home. During conversion, the steady DC current is transformed into oscillating AC current. Modern inverters do more than just convert electricity. They optimize system performance through maximum power point tracking, or MPPT. Solar panels have a voltage power curve where maximum power output occurs at a specific operating point. As sunlight conditions change throughout the day, this optimal point shifts. MPPT technology continuously adjusts electrical parameters to ensure the system always operates at the maximum power point, significantly increasing energy harvest. Many solar power systems also include battery storage, which allows excess energy to be stored for later use. Power electronics manage the charging process when solar production exceeds demand and the discharging process when energy is needed. Let's look at how all these components work together in a complete solar power system. DC electricity flows from the panels to the inverter with MPPT functionality, which optimizes power and converts it to AC. The AC electricity can either charge the battery storage system for later use or power your home and be fed back to the grid. To summarize, inverters and power electronics are essential components that convert electricity, optimize performance, manage battery storage, and ensure the entire solar power system functions efficiently. Most solar systems today connect to the electrical grid, creating a two-way relationship between homes and the utility. During sunny days, solar panels often generate more electricity than the home consumes. This excess electricity is fed back to the grid, providing power to other homes and businesses in the area. At night or during cloudy days, when solar production is insufficient, homes draw electricity from the grid. This two-way energy flow is made possible through a policy called net metering. Net metering allows your electricity meter to run backwards when you're producing excess solar energy. This effectively means you're credited for the excess electricity, allowing you to use the grid as a virtual battery. Grid connection requires specialized equipment to ensure safe and efficient operation. Solar panels connect to an inverter that converts DC electricity to AC for home use and grid export. A smart meter measures electricity flowing to and from the grid, enabling net metering. A safety disconnect allows the system to be isolated from the grid during maintenance or emergencies. Finally, these components connect to the utility grid, completing the two-way energy exchange system. Solar panels are remarkably durable energy generators with an impressive lifespan. Most solar panels are warranted for 25 to 30 years, but often continue functioning well beyond this period. Their lack of moving parts contributes significantly to this exceptional durability. Solar panels gradually lose efficiency over time, with most panels degrading at a rate of about 0.5 to 1% per year. This means that after 25 years of operation, a typical solar panel might still function at 80 to 85% of its original capacity. Several factors contribute to solar panel degradation over time. The three main causes are ultraviolet exposure from sunlight, temperature cycling as panels heat and cool, and various weather impacts, including wind, rain, and hail. Despite these degradation factors, solar panels remain one of the most durable power generation technologies available today, with a significantly longer operational life than many alternatives. Solar energy offers significant environmental benefits compared to traditional fossil fuels. During operation, solar panels produce completely clean electricity with zero emissions. However, the full environmental picture must consider manufacturing and end-of-life phases. The solar industry is constantly evolving, with several promising innovations addressing these challenges. Perovskite solar cells represent a breakthrough technology, offering potentially higher efficiencies at significantly lower production costs. Bifacial panels can capture light reflected from the ground onto their rear surface, increasing energy yield by up to 30%. Building integrated photovoltaics incorporate solar cells directly into construction materials, turning entire buildings into power generators. These innovations are making solar energy increasingly efficient, cost-effective, and environmentally sustainable throughout its life cycle. Through continued research and development, solar power will play an increasingly important role in our sustainable energy future.